last day we saw that the function f of x equals the natural log of x is actually a one-to-one function, and the domain is from 0 to infinity and the range is from minus infinity to infinity. We can conclude that this function, the natural log of x, has an inverse function, and we're going to give that inverse function a name. Before we give an explicit formula for it, we're going to call it the natural exponential function, and we're going to denote it by expx, where exp is for exponential. From the definition of our inverse functions, if you review lecture 1, you'll see that y equals f inverse of x if and only if x equals f of y. So we have y equals the exponential of x if and only if x equals the natural log of y. And recall our cancellation laws. When we compose f and f inverse, we get the identity function. If I apply the exponential to the natural log of x, I get x back again. And if I apply the natural log to the exponential function, I get x, the identity function, back again. Now we can also draw the graph of this new inverse function of the natural logarithm because we're familiar with the graph of the natural log of x. So here I've shown the graph of the natural log of x in blue, and of course the graph of its inverse is this graph reflected in the diagonal of the plane y equals x. And we see that the domain and the range of the inverse function get switched. The domain of our new function, the exponential function, is the range of the natural logarithm. So the domain of the exponential is from minus infinity to infinity, and its range is from 0 to infinity, which is the domain of the natural logarithm. Note that the exponential function is always positive. It's for any value of x, exponential of x is positive because, of course, the range of the function is everything from 0 to infinity. And we see also that since the natural log of 1 is 0, exponential of 0 must be 1. And since the natural log of e is 1, the exponential of 1 must be e. And of course, since the natural log of e squared is 2, that's 2 times the natural log of e, we get that the exponential of 2 is e squared. And since the natural log of e to the minus 7 is minus 7, we get the exponential of minus 7 is e to the minus 7. And in fact, this works for any rational number r. According to our laws of logarithms, the natural log of e to the r is r times the natural log of e, which is r. Therefore, the exponential of r is e to the r. Now we know that the exponential of x is e to the x when x is rational. And remember that we haven't yet defined e to the x for x irrational. And we can use this new continuous functions to join the dots and make such a definition. So we define e to the x for x irrational to be the exponential of x. And that is, it's the unique number e to the x for which the natural log of e to the x equals x. This should agree with other definitions of e to the x that you might have encountered which use limits, since exponential of x is a continuous function. And now we have a complete formula for the exponential of x, namely the exponential of x is e to the x. So let's restate the above properties in this new light of our formula for the exponential function. We have the inverse function for the logarithm function is now e to the x. We actually have a formula for it, where e is this very special number where the natural log of e equals 1. And we have e to the x equals y is the same as saying that the natural log of y equals x. And we also have from our cancellation laws or our composition laws for f and f inverse, e to the power of the natural log of x is x, and the natural log of e to the x is also x. So this last formula is very useful in solving equations because we can use the exponential to cancel out the logarithm, so to speak, and the logarithm to cancel out the exponential. Here's an example. Suppose I want to solve for x if the natural log of x plus 1 is 5. So I want to get past that logarithm function and solve for x, and I use the exponential to do that. So I take e to the power of both sides, or apply the exponential function to both sides, and I get e to the power of the natural log of x plus 1 is e to the 5. And now, using our laws that say e to the natural log of something is that thing itself, we get x plus 1 on the left-hand side equals e to the 5 on the right-hand side, and then we can solve for x as e to the 5 minus 1. Of course, e to the 5 is an actual number, so we've completely solved for x here. In the same way, if we have an equation that looks like this and we'd like to solve for x, then we can apply the natural logarithm to both sides. So we have the natural log of the left-hand side equals the natural log of the right-hand side. And the natural log of e to the x minus 4 is just x minus 4, because the natural log of e to the u is just u, no matter what u is. And the natural log of 10 is actually a number. And now, bringing that 4 over, we get x equals the natural log of 10 plus 4.